surface tension. So we're going to go on to the thing that you might have been expecting in bionics or surfaces. Surface tension is an emerging property of the forces between molecules. So if we have a liquid with forces between the molecules, we will discover that there is a surface tension too. And the surface tension has a certain power. So we can measure the surface tension. That's dependent on the area of the surface. And if we compare that to the size of a drop of liquid, for example, we can see that if we increase the size of the drop, the weight, the mass of it, will go up by the radius cubed effectively, and the size of the surface will go up as a factor of the radius, or the radius squared, depending on whether we're measuring the area or the length of the perimeter. If we plot those out, we can see, as on this graph here, that they cross over at a certain size. So below a certain size, surface tension is stronger, and above a certain size, gravity or mass is stronger. This is particularly important for water. For us as humans, water is the most important liquid, and what we find is that this crossover is somewhere around 2.5 millimeters, which means that the diameter of a drop that was exactly that size would be around 5 millimeters. If we look at raindrops, that's about the standard size of a raindrop, because as it falls through the air resistance tears the drops apart until they get to about 5 millimeters. Not always exactly 5 millimeters, but close to. If we throw a block of water out of a plane, so we're trying to put out a fire, it will automatically split up as it accelerates down and eventually make about the same size as normal raindrops. If we go into space where there's no gravity, then we can make much larger drops. They're obviously extremely fragile, because then other forces such as the inertia of the drop and any surface waves or any wobbling that it has become larger as the drop gets larger. But you will all have seen videos of astronauts fiddling with a blob of water. While we're on this page, or this is my paper by the way, while we're on this page of my paper, we can see a couple of examples of things exploiting surface tension. So if we have a piece of metal and we make it small enough, it will not sink, as long as we balance it on the surface tension of the water. So on the far right there is a picture of a paperclip that's floating on water. It's not really floating, it's supported by the surface tension. The spider is an underwater spider, and it has a layer of air supported by surface tension on its abdomen and thorax, and that uses that to breathe. A simple way of looking at surface tension is to imagine a force per unit length inside the liquid pulling at the surface. This is how we can model it. It's not the best way of doing it, so it breaks down in some conditions, but it's a good model. Traditionally, we could measure this surface tension, or we still can, by taking some liquid in a trough and having a flat piece of metal, typically, on the end of a wire, and pulling it out of the liquid. At the moment that the liquid snaps and lets go, we get a measure of the surface tension, which is the extra apparent mass due to the water or whatever liquid it is pulling down on it. Only at the point where it detaches, and only if it was stuck to the corner of the metal or whatever the plate's made of, only if it was stuck well to it, does it work properly. But practically it's relatively simple to do. The problem obviously is soap and any contamination. It is practically not so easy to make sure that our liquid is pure beforehand. So now that we can measure the force of surface tension, we can do something with it, which would be to try to work out why drops do what they do. If we imagine a drop of water like this on a surface, this is a quite water-repellent surface, which is why it's sitting up as a drop. We can imagine that there's a complicated relationship. The volume of the drop is fixed, and then the surface area should be minimized because the surface tension exists. So there's a force or an energy required to make new surface area, so that will be minimized. Then there's an interaction with the surface, and there are pressure constraints. The pressure inside the drop has to be the same everywhere, apart from it can be higher at the bottom than at the top, but it has to agree. So the pressure inside bends the surface tension, bends the surface, and it all has to work out mathematically. That is obviously going to be very difficult to solve, although it is possible. We can look at it in a far simpler way by just looking at the forces at this corner here. If we look at the forces at this corner here and imagine it moving a tiny amount, that doesn't affect the volume of the drop or the volume of the shape very much, and so we can assume that's negligible, and that allows us to come to a good approximation of what happens at the edge of a drop. So this is zoomed in, this is our drop, this is the air, this is the solid, so we're just looking at it a little bit, so obviously it continues in this direction more. And what we can see is, or what we can draw on there, is the surface tension, which will give this letter gamma. Gamma LV for liquid vapor, and the reason that we've called it gamma LV is because we need two others, because there is also a surface interaction of the solid, which is pulling in this direction, and a surface interaction of the liquid with the solid, which is pulling in this direction, which I'll draw on. Sort of. It's quite hard to draw it sideways. So we've got the surface tension, or the interfacial tension in this case, between the solid and the liquid, and the interfacial tension between the solid and the gas. There are differences between these two because the solid can't move. So the interesting one is the liquid vapor, and the interesting point is this contact point, because this can move along the surface. If we also approximate and say, assuming it can move wherever it wants, because the solid can't move, we don't need to worry about the vertical components of these forces. So all we have to do is add these two together to see what we get left over, and that should be equal to the horizontal component of this, which we can do fairly simply with angles and vectors, although we do need to know one of the angles. So we will choose this one, the inside angle of the water, or drop, and we will call that theta, because that then agrees with a lot of standards. Doesn't really matter what we call it, sometimes it's called alpha, but we'll call it theta here. So I've jumped a step because normally we would draw a right angle triangle on this side to measure the component of force, so let's do that. So first of all, make this angle less than 90 degrees. If we want to know the horizontal component of this force, we would need to know the length of this side. It's a right angle triangle, and that would be the cosine of the angle multiplied by the length of this longest side, which is good, because if we increase it over 90 degrees, which is the one that we've got in this example, the cosine goes to negative, which for the purposes of this particular maths is really handy, because it means that the vector is pointing in the other direction. So the maths works out whether it's pointing in this direction or in this direction. What it doesn't work out is if we go over 180 degrees or less than 0 degrees, because then we're inside the solid, so then it doesn't have physical significance. We always have to consider whether our equation that we're using loses physical significance at some point, and in this case, above 180 degrees and less than 0, that half a circle inside the solid is not always relevant to reality. So what we can see is the sum of these two minus the component here, but it's minus of a minus in this case, so plus that is equal to 0, which means that there's no force on this point sideways. If there's a vertical force, we're assuming it doesn't do anything. It's not 100% correct to do so, but in most cases it works. So we can form this equation, and we can rearrange it by adding this to both sides, so move it over to the other side, and then dividing by the surface tension of the water, gamma LV, and that gives us an equation which is formerly known as Young's equation, although it wasn't actually formulated by Thomas Young, the person referred to in Young's equation. It actually came about later, but he did talk about it and was very close to doing so. So if we resolve that, we get this equation. The cosine, because the cosine of this angle is equal to this simple equation of the surface tensions, but only if we're considering them as forces. So there will be some assumptions. Obviously, the assumption that we've already had is that this point is allowed to move over the surface, but only horizontally. In practice, what we see on real surfaces is that there's a range of angles where a drop will be reasonably stable. So if we look at a drop on a piece of glass or a piece of plastic, what we find typically is that it doesn't have a single angle where it sits. If we add more water to our drop, we will push the edge over, and it won't jump until it gets to a certain size. And if we suck water out, or we allow it to evaporate, it goes back first, it tilts back, and then it jumps back. This is called hysteresis. It means there's a variability in the angle before it moves. If we take that to an extreme and imagine a drop on a window that's vertical, then we can see that it typically hangs in this shape, from the side obviously, and this is important because the force that's required to hold the drop up against its weight, so there's a force from its weight downwards, and there's a force from the surface tension upwards through this point here and the point on the top. It doesn't actually have to have this one folded right over, sometimes it's not, so it could also be a drop that looks like this, but there has to be a difference in angle between the back side and the front side to generate a force that is opposing the force of gravity. If there is no difference between the front and the back side, it doesn't matter what the angle is, the drop will fall down, or slide down is better. So if it has a very high angle and a very low difference in angle, a very low hysteresis, it will slide down, and that is what we see on Teflon, for example, PTFE. A drop will slide over a surface of PTFE relatively easily. You need to exceed a certain size for the mass to be enough, because the length of this line, or the length of this piece that's holding it up, is dependent on the volume, on the radius, and the mass is again the radius cubed. So we again have an effect of size, that small drops will stick anyway, but above a certain size they will slide, and the size, the threshold size, depends on the difference between the two possible angles. If it's Teflon is very small, there's a very small difference, but if we take the glass and we make it very, very clean, then it is also very, very slippery, but the angle is extremely low. It's below 10 degrees, depending on the exact type of glass, so I can't draw that, but it would be like that, and it would slide down the surface as well, because there's very little difference between the front and the back edge, because it's clean. If we make our imaginary surface rough, then we're increasing the interaction area between the liquid and the solid. So let's draw our liquid on again. And we are increasing the interaction area, so all of this is interacting instead of the flat area. In order to account for that, in our same equation, with the force from here, the force from the solid-liquid interface and the force from the liquid-gas interface, we need to increase these two horizontal components by a factor of the roughness, the extra surface area that we have. That gives us another equation, which is logically exactly the same. So we've got the cos of the angle is equal to the roughness factor, which we call R, multiplied by 2 surface tensions. What's important is obviously this one, the surface tension of the liquid, is not changed by this roughness factor, which is just the multiple of the area that we've increased it by. However, the other two are. That gives us this new equation, which is equal to, which tells us something, tells us the cosine of the angle on our new surface is equal to the roughness factor R multiplied by the cosine of the angle on the flat surface, which is over here. So that's just substituting the other equation. What that tells us is that we've got a change in the angle, but it's a change in the angle that's mediated by this cosine function. And that's important because if we increase r, the roughness, we can easily make it so that our contact angle, the theta that we would calculate coming back out, will be greater than or less than the allowed angles. We'll end up with angles that are higher than 180 degrees or less than 0, which will cause our equation to not work. So what happens if it passes 180 degrees? We go past that, then we reach a state where not going into the 4s can be advantageous. It's not exactly the consideration that's required, but it is one of the possibilities. So if we have a very high roughness, then very often it won't be fully wetted if it's hard to wet to start with. If it was easy to wet to start with, it will wet completely. But let's start with this case. In this case, we've got gas in here. We've called vapor or gas because I've got my letters confused. And we've got solid. So now we can consider, instead of having a roughness, which was an increase in surface area, we've actually got a decrease in surface area. And so we're going to multiply by a fraction instead of by a number that's greater than 1. In this case, we're going to call it f for fraction because that is what you will see in other examples. So it's good to keep it the same. Because in this particular example, I've made it flat on the top. Then we've got a fraction that adds up to 1 so that we end up with the same area. It's exactly the same area as it was before. So we've got a fraction f, and the other part of the surface, which is the whole, is equal to 1 minus f, the rest. So if we look at this again, we started with this equation last time, which was the bit underneath, just this piece, minus the bit outside, which is the force from outside, plus the force from the vector of the surface tension. And now we're going to have to multiply this bit here, by f, because that's the bit that changes. But this has ignored so far the bit 1 minus f, which is the holes, so we have to put that back, otherwise we don't have as much surface area, and that is going to be this area here, which will appear on either side. So in this case, it's just this piece here, which we're interested in, and that has to be added onto here, so that we come out correctly, and we make our equation all ugly. But we can simplify it again by moving these two things to the other side, and we get a new equation. I've just noticed I did the signs wrong, so these are negative to make it the same as last time. What I've done was I switched these over, which changes the signs. So apologies for that. It's better to have them the same in the same talk. So if we move those two over to here, we can now, we leave it like this. Okay, so to recap, we've got the piece that we had before, which was the difference between the surface tension of the solid pulling our line out, and the interfacial tension between the solid and the liquid pulling it in, and then the component of the surface tension pulling the line forwards or backwards. That was the original one. Now we've modified that with two extra terms. We've multiplied this by a fraction, and we've added an extra term for the liquid vapor bit that appears underneath. Then, if we rearrange it, we can put the cosine theta on the other side, like we did before, and divide by gamma LV to get this all neat, to have the same form, gamma LV, and then we can simplify, so we can have this as these two bits, gamma LV and gamma LV, which we do because these two cancel, which makes it nice, so we can get rid of these terms here. And that leaves our somewhat ugly, but more changed formula for the case where it's hanging over the top. So we've got a smaller term on the top, which is divided by our liquid vapor, but we've got an extra term from the bottom of the liquid. That's enough for one time, because otherwise we'll go on too long. The treatment here is just forces, and it's the comparatively simple way of doing it. Actually, it's better to do it with surface energy, which gives you an area component as well, but it works better mathematically and psychologically, logically, but the forces argument is mathematically shorter, which is what I've taken it here. And the first part of it, the starting part, is much more obvious.